So far, we looked at two ways of proving things, natural deduction and truth tables. And you notice that it was faster to solve the puzzle that we did using natural deduction than by writing a whole big truth table. But is it always better? Can you always get a shorter proof by using natural deduction than you would by writing a truth table? And the answer is, it's a very, very good question. And moreover, it's very closely related to the question of how fast can one check if something is a tautology. And you might remember that this is a $1 million question. There is $1 million set aside specifically to somebody who can figure it out. So if you could figure out whether natural deduction is always faster than the truth table, you may get the $1 million. Wouldn't that be cool? So as computer scientists, we don't just want to figure out how to prove stuff. We want to figure out how to write programs which will do the proofs for us. Oftentimes, it's the next level of thinking. First, you try to understand with the general rule how you could solve it, and then you sit down and say, how can I actually put it in words and then in code in order to make a system that would solve the problem for me, no matter what kind of formula, what kind of premises, conclusion I will give it. So truth tables are very easy to program. If you know even a little bit of programming, you could just sit down and write a program that will fill in the truth table cell by cell, and it's not difficult to make it correct. But the proofs are enormous. Remember, if you have n variables, that you will have 2 to the n lines in your proof, which is already too big when your n is something still pretty reasonable, like 10 or 15. Natural deduction, on the other hand, can give you smaller proofs. But how do you program it? And again, it's a very, very good question. If you could figure it out, well, even if you don't figure out the whole can you find a smell test for tautologies, but you do figure out how to make natural deduction work, you could probably make $1 million pretty quick, because a lot of companies out there will be begging you to come and work for them. We don't know, even if there is a small proof in natural deduction, whether we could find one quickly. It's a very active area of research, kind of cutting-edge computer science research. And this is something that you can already think about even after only a few lectures of this course. So, how do automated provers that we do have now work? Because we actually do have a lot of provers, people who are making hardware, people who are making new chips, they're using those automated provers to verify that their chips work correctly. People who design aircraft use automated provers to try to check that their aircraft are not going to do something dangerous. Even people who schedule exams at universities, they use automated provers in order to make sure that, for example, a student doesn't get scheduled in 2 exams that are happening at the same time. So lots and lots and lots of application for automated provers, and most big companies right now have their own provers, and they try to improve them. So how do they work? So first of all, automated provers nowadays, they work with a special kind of easier formulas, which are product of sums or CNF formulas. So here's how those formulas look like. The very top of your parse tree would be an end. It's the end of a whole bunch of constraints. And every constraint is of the form or of a bunch of things. So your formula looks like this. So this happened, and that happened, and that happened, and that happened. And each of those things is either this or that, either this or that, and so on. So moreover, each of those ors only deals with very simple formulas, which are either a variable or a negated variable. So here are some examples. y or not z and not y and y or z. This is a formula in the CNF form because it's an and remember we could draw the parse tree for those things with a lot of things connecting to the same and a lot of things connecting to the same or. So we have 3 parts which are all connected by an and. We call those parts clauses, and each clause contains several what we call literal variables or negated variables. Even if you have just one or of variables, negated variables, or an and of them, those would be CNFs. Then your very top and would contain only one thing, or your ors would contain only one thing, and that's fine, that's still a CNF. What you don't want to have is something like X or not Y or Z, because in this case you have an or on top and an and underneath, and the CNF structure does not allow it. Engineers sometimes refer to CNF as product of sums. So if you're doing logic design and circuits, you will probably see an expression product of sums that means the same thing. The term CNF itself comes from expression conjunctive normal form, where the word conjunctive stands for and. It's just a fancy way to say an and. Don't need to worry about conjunctive normal form, but we will use abbreviation CNF a lot of times. So just to say again what the notation is, if we have a variable or a variable with a not in front of it, remember because of double negation, we could always have a single not or none, and this will be equivalent to having respectively even number of the negations or an odd number of the negations. We would call this thing a literal, and we would call it a positive literal if it doesn't have a not on it, and negative literal if it does. And we will call an or of literal a clause. We could also talk about an empty clause which has no literals in it. That is, there is something hanging in the tree which is like an and, it doesn't have any children. It's kind of not what we allow it to have on the tree, but we could still give it a meaning. Remember, if we have an or of variables, that or will be true if at least one variable is true. If we have no variables in there, we cannot make it true. There is nothing there that can make it true. So an empty clause, an or where there is nothing, is the same thing as false. Another thing is that if you put a variable and negation of the same variable together in a clause, then you get something that's always true. Because no matter what, either X will be true or not X will be true, and you really don't care what else is in the same clause. So we will sometimes write for clauses C and D, things like C or X and D or not X, or even C or D, and what we mean is just a bigger or which has more literals. For example, the first one will have all the literals at C together with a literal X. And symmetrically, if you take an and of CNF formulas, you also get a CNF formula, because you're really not adding extra nodes to your tree. All you're doing is you're connecting more things to the same top end in the tree. Okay. So you say that might be all good, but how do we actually get a formula in CNF form? Lots of ways. I'm showing you a simple one. In industry, they have more complicated ways of doing it. But one thing you could do is you could just rewrite it using and or and not using equivalences. You already know by now that A implies B the same as not A or B. And similarly, A if and only if B, you could write as not A or B and A or not B, and you get a CNF formula. But what if you have something where you have F or an and of two things? Here, we could use that rule for factoring things out backwards and say this is the same as f or g and f or h. Now, if f was a clause and g was a clause and h was a clause, we end up with something that's a CNF. Okay, let's do an example. So suppose we have P implies Q or R, and here is a parse tree for it. The first thing we will do is we get rid of the implication by replacing it with not the first thing or the second thing. And here it is. Now it's not a CNF yet because we have a OR on top and below it. So we can apply that last rule about taking F inside the parentheses together with G and separately with H to get the new formula, which now is finally a CNF. You see, it's a little longer than the formula that we started with. And this is kind of the price that we pay to make the formula simpler to deal with.